So today I'm going to talk about data quality in ML pipelines. So my name is Pritam Dodeja, and I'm an engineer, machine learning engineer at Intuitive Cloud. And then we see data from a variety of contexts, right? Whether it's IoT data from energy or video data from healthcare, et cetera. So data at scale is effectively the problem that we work on, day in, day out. So let's define the problem of data quality. Like, what does that mean? What can we do about it? And then what have we done so far? And then what still remains to be done? So, data untracked is a problem. So each example that you're training on, how do you know, like, where it came from, what it is, and how it's performing, like what it's introducing into your pipeline? An analogy of this is you wouldn't travel without a passport. But often we treat features like, hey, this is, I'm going to normalize this, I'm going to do this, I'm going to do that. But what about the example, right? So we need to give passport to data. We also have a boarding group when we fly. But yeah, in data, we don't really track what split this is part of. We just say this is an example, right? We have to go through security when we fly. But for data, we just say, hey, just go into the gradient descent process and it's all good. Well, you're going to hit turbulence, right? And then we generally stay with our traveling party when we travel, right? So we make sure that things don't get jumbled up. But how do you keep things together if there's no identifying characteristics? Imagine, a million taxi cabs converging on a point and not knowing where each came from. How can you manage the security threat that's potentially in one of these? How do you manage that, right? So at scale, this is something, and Beam, being what it is, enables you to solve exactly these types of problems. So an analogy here would be, your entire trip, you can think of that's the ML pipeline. Your passport is an example identifier and the value of a feature. A boarding group is your split. Your population demographics are your statistics, or the quote-unquote shadow. Then the description of the traveling party is what you expect of the data, the schema. The traveling party itself, the group, is an example. A luggage tag could be like a data quality feature. That's something that you're adding. A security check is something that you make sure that data is good. And I'll define that in the rest of the presentation. Then, the check-in into the gradient descent or the flight is the transform features. Like at that point, you want really clean data. The population is the entire data set. Now, just like you wouldn't stare at the sun, you would blind yourself. Being able to see entire data is not possible for us, but it is possible for Beam, right? So we can kind of try to bridge the world of the sun and the shadow if we manage our data properly, right? And then the subpopulation of the data is a slice of the sun, a little beam that we could analyze without blinding ourselves. So what are the challenges in data quality in ML pipeline? So this is, I'm not talking like before, but once the data hits the pipeline, what are the challenges? So data is inside the pipeline. It's optimized for flowing fast. It's not optimized for like observability, right? And we are outside the pipeline. We don't get to be in there. Data is very large. It's very messy. There's a variety of formats. There's a format that's optimized for reads. There's a format that's optimized for the gradient process. Then it's hard to see the connection between the data and its effect on the models, because usually it doesn't have a thing that, it goes in batches, and then the batches have influences, but then you can't see like in the batch which was the culprit, right? That's a problem. And good data is hard to find. Like in our code bases at Intuitive, we see that more than 85% of the code is actually data processing code. It's not ML code. Literally, like, we do counts, like it's like less than 5%. Yet that's the focus of like, hey, there's, the transformer has been invented for a long time now. You can plug it in for any sequence thing. It's great at finding patterns, right? So we plug in the transformer. But the attention of like on the 95% of the work, that I feel that needs more of the focus. And that's where Beam, based on its data flow model, enables you to do exactly this. So if I had to track a billion photons, I would use Beam to do it, because that's the platform built for it. So, and why is that? So Beam speaks 1,000 formats. No data is outside of Beam's reach. Beam plus TFX, this particular pipeline I'm going to show you, they reduce the surface area of the skills that you need to have in order to do this. You don't need to be an expert in all different parts. You can abstract those. And if you want to go deep into a part, you still can, right? But abstraction is good because abstraction enables people to work together and specialize. Then Beam, with its ability to execute UDS on behalf of the user, can really simplify the data processing. It can scale it, but it can also enable an easier mental model for the users, right? And that making things easier for the user while scaling, while improving things in an orthogonal fashion is, in my opinion, the way to kind of win at this game. Then TFX is a component architecture which can manage the end-to-end trip. So the hardest part in the ML pipeline, in my opinion, is the management of the metadata, right? Because if you can't track your artifacts, you are in a dark room trying to find the treasure. You can't find it. But the moment that you have artifact tracking and metadata management and automation of that, right, that's when you really can get good at things, right? And then the concept of a pipeline as a thing, in my opinion, makes it hard to inspect different parts of things. Because a pipeline is an end-to-end thing in ML, kind of you put in the data and then the model comes out on the other side. What about all the intermediate steps? So what we want to have is like have our cake and eat it too. We want the end-to-end pipeline, but we want to be able to open up that pipeline and inspect data as it flowed through, right? So how Beam helps kind of in the different aspects of it. So at pre-ingestion, you can determine the schema from data. Determination of schema is a distributed computation problem that can easily be solved by Beam. Data splitting and identification. Here you can partition the data using Beam, and it can do that. And there's other standard components, kind of encoding of examples, computing statistics. These are things that are standardized. It's just what is the data format, and Beam speaks all data formats. Data exploration. So some of the things that we built is like, how do you open up the pipeline? So we built this component called a JSON sampler, and it uses Beam to basically sample what's flowing through the pipeline at different stages. Then we built another component called a PreTransform, where you can apply an arbitrary Python UDF as the data is flowing through the pipeline, such that we can inject things. And the things that we inject will have to do with data quality. And then if we're injecting things, the reason we're injecting things is to actually remove bad data, right? We want to be able to kind of have a marker, right? So we want to kind of break it up into multi-step process because we may want to inject things for other reasons, not just data quality. So here's an example of how schema generation can work in Beam, using Beam rather. So you have some data, and then you have this YAML library has this function called YAML.saveLoad. So you can load each element and have YAML.saveLoad interpret the type of this element, and then you can track of all the elements how many for each position or each key that you had, how many different types of did it take on. It was an int 70% of the time, a float 20% of the time, and string 1% of the time. Then you could say that, hey, likely this thing, the only way we can encode this thing is a string. Right, so there's a deterministic way of like solving for the schema, assuming that your data is not corrupt at the beginning. So if we make that assumption, we can compute the schema, and then you see at the bottom here, there's a my record class. This was generated by Beam itself, which went through all the rows, and that's what you see in the intermediate step. That these are the counts for the various features. Then the next thing that now we have something that's strongly typed. So with schema-aware P collections, we have the type, right? Now we can use that to generate a UUID. We can give it a passport, right? We have that UUID injected in the record itself. That's why our objects have those UUIDs. And then we can actually, so in this case, the data was like 25, 30 million rows. Right, so Beam can do approximate quantiles to do the splitting of data, right? But with compiled languages such as Go, for 25, 30 million rows, within like less than a minute, you can compute exactly what the quantiles that you need, right? So you can use a compile language and then determine the split and then split your data using Beam. So the scaling aspect of it is kind of interesting with the splits, because if your data's, I wonder what are the boundaries at which something like Go doesn't work, right? But another thing that I think of is the split itself should be managed as metadata, because if you're going to be doing this split, what did the split, what was the split for this run, etc., right? How do you manage that, right? So that's where kind of the metadata management becomes like very important. So now you have all this data, and then you get the statistics of this data. And this is kind of like looking at New York from South Jersey and saying, hey, let me make sense of what's going on in New York, right? To me, that's kind of like most people hit this wall, right? And wouldn't it be great if we could zoom into this, right? So that was the inception of like us building this. So how do we zoom into this, right? So in a sense, the statistics are the shadow, but we can't stare at the sun. We don't want to go blind, right? So what we can do is we can sample parts of the sun, the little beam. And then for this, what we've done is here you see this particular name tuple generator. So this function, right? What it does is it takes in a class name and a schema. And in this case, the schema has been computed by statistics, right? And then it says, okay, if you are, and there's protocol buffer names that I probably should put here, but if you are this type, then let me create a proto dictionary, like a shadow of you of this particular photon. Let me make that, and then let me create on the fly a name tuple object that I can, register with the beam itself. So then in the pipeline, when I'm constructing my pipeline, I have this object, I've registered it, my data conforms to the schema, and this object is actually managed under ML metadata. So here you see that I'm going to my store, I'm saying, hey, what are all the artifacts of type JSON sampler? And then I can kind of get that list of artifacts. So then now we can actually interact with a beam of light and also see kind of like the shadow of that particular sliver of light that we're dealing with. So now we can actually zoom into that view of New York, and we can see New York from maybe Hoboken, right? But I'd like to get to the next level, which is something, because we have the UUIDs, right? We have passports on each of these points. So we can actually zoom in more. And here's a thing where Beam might be able to help. Where, like, let's say you wanted an infinite zoom feature. That would be cool. So now what we do is we say, okay, let me zoom in, and then I'm going to inject data quality features. So here you're seeing that, okay, on this histogram, I'm going to get like the boundaries of this histogram, and then I'm going to put those, I'm going to track these, right? So I get these boundaries of this histogram, and then I can enable that filter, and then I can get the Python equivalent of those boundaries, right? And then I take that Python equivalent and I push it into my UDF, right? I'm going to inject these data quality features, and this UDF basically takes in a dictionary and returns a dictionary. And what does it do in the middle? So coming in is an encoded example. We explode that because we know the schema, right? We can on the fly create a native Python dictionary for Python primitives. If your data is high dimensional, there's other things you could do. But we can explode that, get a native Python representation, apply this particular UDF, right, which injects in data quality features, repack that back as a TF record, and then send it downstream, right? So, and then we place that in our pipeline, and then we put in, now that we have this PreTransform version, we once again do JSON sampler and the rest of the stuff. So statistics, schema, all those things go into our JSON sampler, and then we sample that refined, not yet refined, but rather enriched data. Then we can, so the scaling of this, right? So Beam is a monster when it comes to scaling. So here you see this particular PreTransform run, and this was on like 25 million rows. So in 56 minutes, it did, about 1,200 minutes worth of work. So it's 7.3 thousand injections of data quality features per second. So this is beyond, like, so what we can actually visualize on that is about like 25, 50,000 points, right? So in a few seconds, what it's doing is beyond like what we can visualize. But this parallelization by Beam is the reason why massive data at scale for machine learning, there's no better platform than Beam, because that worker has access to all the resources. So then what do? Now we've injected these features, we subtract. We've added, now we have to subtract. So here, this particular function, filter function, takes in our schema, and then for each data quality feature, we just say, you know what, I just want good data. Anything that doesn't meet the data quality kind of characteristics, we just subtract that, and then we're just getting, once again, our TF train example, and then once again, we're putting a JSON sampler, etc., in the pipeline. So now we go with, now this is the view, right? Now we are no longer having points that are all over the place. And we can see the statistics of a particular data quality feature, and we see that it's always 1 because all the zeros have been filtered out. So downstream pipeline components then can use this enriched version of the data. I'm not saying this is the purest form, but it is a form of data that is pretty pure. Now we want to hunt bad examples, and that's something that I want to kind of enhance this. But now we can feature engineer our data. We can place our JSON sampler on the feature engineer data for like low dimensional stuff. For high dimensional stuff, we still need to solve for that. Then we have UUIDs. We can have fine-grained tracing of the impact of each example. So what was the loss for this particular example? We can actually track that because there's bulk inference that you could do. So the forward pass of your gradient algorithm, you can see kind of like what that effect was, and that can become another input into your filtering process. Because let's say you had values that fit within the statistical bounds of what you think is good, but are flipped. What we've done so far won't catch it, but gradient descent will catch it. So you can have like a sentinel model that does filtering. So models trained on this have lower loss. And I'm not, the talk today is not so much focused on the models, but rather on like the data quality. But ML metadata is what is enabling all of this to work. So now we see transform statistics. And now we can actually see the overlap across these distributions. And we've done this at 20 million rows, but Beam, if this was 200 billion rows, this would not be a problem for Beam. Right? So as a mental model, being able to look at the shadow, interact with it, and then applying the scale, and then you can take this and plug it back into your sampling, and you could see that, okay, let me see in my subpopulations, are there any deviations that I can catch? So how can we make this better? So in pre-ingestion, we can, currently I'm using a direct runner, but this can be done on other runners. This utility code for schema generation can do better integration of the UUIDs. You could do the UUIDs after the split instead of before. There's some things that could be improved. You could, in data splitting and identification, you could manage the split point in metadata, the splits in data itself. We can then we can have a component for temporal data, for time series data, so that Beam can figure out these things and split the data for you. Then in data exploration, we can have multi-dimensional support. So the James Webb feature, right? Like you have your data, and then you're zooming into a particular space, and then Beam is doing those computations and interacting with the visualization engine, right? That's something that is a distributed computation problem, because the way that that visualization engine works is that you interact on the map or the histogram, and then it is tracking those UUIDs and subtracting those. Right? So it's in a sense tracking those cabs in real time, and then you can basically interact with it from both the actual thing as well as the shadow of the thing. Then the non-graph intended feature injection, this naturally supports polygons. So if you wanted to cut out a section of the river, right, you can actually draw that polygon, put that in your UDF, right, which you cannot do using these more contiguous bounds. Then in filter, we could store filter data as a managed artifact. Right? What data did we subtract? Today, I'm just producing those splits that are purified, but I also want to see the bad data. And then building sentinel models that enforce data quality. Right? So far, we've done more human-driven data quality, But once the model learns, for like even a minute of gradient descent, we'll teach it to learn how to spot bad data in a more sophisticated manner. So these are the transform statistics. The top left one is interesting because it speaks to the direction that the cabs took. So that's, to me, that's interesting. And this is over 2 years. So the behavior, the human patterns, how much they overlap over 2 different years, to me is a sight to behold. And then a demo. So unfortunately, I don't have time for the demo, but I do have a fully working pipeline for this. In fact, this pipeline, I was working on time series data, and then two of my coworkers, they won the hackathon at the Beam College, and I'm not one to be upstaged. So I threw out my time series code, and I said, you know what, I'm going to build some stuff for the Beam Summit so that Aditya and Darshan can know that I'm, as a boss, I do not like being upstaged by them. So my time is up, but I sincerely appreciate the opportunity. I thank the community for building these amazing data products that are solving the problems at a global scale. And I think Beam is definitely one of these products.